Welcome to the Deep Dive. We dive straight into the big topics to get you up to speed fast. Today, we're definitely aiming high, looking at something massive for American spaceflight, the Vulcan Centaur.
Yeah, it's a big one.
It really is. This isn't just, another rocket. It's United Launch Alliance's brand new, super powerful next-gen launcher, and it's designed and, importantly, certified for America's most critical missions.
Exactly.
So we're going to dig into where it came from, what makes it tick technologically, some key missions it's already flown, and crucially, why it's becoming the go-to rocket for the U.S. Space Force and really for American space access overall.
That's the plan. Our mission, if you will, is to really unpack why this specific rocket, built here in the U.S., is so incredibly important right now. We'll look at its history, its design, the tech inside, those milestone flights, and, yeah, its future. And what's interesting is how Vulcan ties directly into, well, bigger U.S. strategies for national security and the commercial space race.
Okay, let's get into that origin story then, because it started, what, back around 2014?
Yeah, about then.
And its development wasn't just about building a new rocket, was it? There were these two really powerful drivers behind it, both deeply connected to U.S. interests. First off, there was a clear mandate from Congress. The U.S. was, well, frankly, in a bit of a tricky spot, relying on those Russian RD-180 engines for national security launches.
A strategic vulnerability for sure.
Definitely. So Congress pushed and pushed hard for an all-American engine. Get rid of that dependency.
And that links right into the second major driver. It wasn't just about getting away from foreign engines, although that was vital. It was also about competition. The space launch market was changing fast.
You mean SpaceX?
Primarily, yeah.
Okay.
ULA, United Launch Alliance, they've been a stalwart for decades, launching government stuff, commercial satellites. But they needed something new, something to compete head-on with SpaceX's Falcon 9, which was, really shaking things up with reusability and lower costs.
So Vulcan had to tick both boxes. Strategic independence for national security and be competitive commercially.
Precisely. Ensuring America stayed ahead in launch capability.
And it wasn't just about facing new rivals. Vulcan was also stepping into, well, enormous shoes.
Great shoes.
It's replacing two absolute legends of American rocketry, the Atlas V and the Delta V. Both incredibly reliable, decades of service.
And both winding down, set to retire pretty much now mid-2024.
So Vulcan isn't just adding capability, it's taking over the core launch needs for the U.S. government, a complete replacement.
Absolutely. And its goals reflect that. It's designed for everything.
Yeah.
Top priority national security launches for the DoD, big NASA science missions, commercial satellite deployments. The whole focus was make it super reliable, make sure it's all American components for supply chain security, and make it cost-effective enough to compete.
Which leads to the question, how do you actually build one rocket to do all that?
Good question. Let's look under the hood, so to speak.
Yeah.
At its core, Vulcan Centaur uses a two-stage design. Pretty standard, proven approach for getting to orbit.
Okay, so stage one, the booster. How big are we talking?
It's substantial, about 33 meters tall, so roughly 11 stories high, and 5.4 meters wide.
5.4 meters, like a standard semi-truck trailer width.
Exactly, that kind of scale. A big cylinder. And powering this first stage are two BE-4 engines. These are methane and liquid oxygen, or LOX engines.
Man, okay, that's a bit different.
It is, and it's a key bit of tech we'll circle back to. But the power. Each BE-4 pushes out about 550,000 pounds of thrust at sea level.
Wow, that's a lot.
It's immense. Think like 12 jumbo jets taking off at once, just for those two engines. You need that raw power to get moving.
But that's not all the power it can have at liftoff, right? It's modular.
Correct. That's a huge advantage. They can strap on up to 6 solid rocket boosters, SRBs. These are GEM-63XL motors. Each one adds another kick, roughly 460,000 pounds of thrust.
So you can basically dial the power up or down. 0 SRBs for lighter loads, 6 for the really heavy stuff.
That's the idea. Tailor the rocket and the cost to the specific mission needs. Flexibility.
Okay, so booster stage, SRBs, then the second stage.
That's the Centaur V. Same 5.4 meter diameter as the booster, but shorter, about 11.7 meters long. It uses liquid hydrogen, LH2, and liquid oxygen, LOX, as propellants. Highly efficient stuff for space.
And the engines on the Centaur.
That's where the heritage comes in. 2 RL-10OC engines. These things are legendary. Over 400 successful flights on Atlas and Delta rockets. Their big advantage is restart capability.
Meaning they can shut down and fire up again in space.
Multiple times, yeah.
Huh.
Absolutely crucial for complex missions like adjusting orbits precisely or sending a probe to the moon or beyond. They offer incredible precision.
So all this combined, the stages, the boosters, what can it actually lift? What's the payload capacity?
Well, with that flexibility, 0 to 6 SRBs and different size fairings, the nose cone protecting the satellite,
Right.
it's definitely a heavy lifter. With 6 SRBs, it can haul about 14,500 kilograms, that's over 30,000 pounds, up to geostationary transfer orbit, GTO.
GTO. That's that high orbit where communication and weather satellites often end up.
Exactly. It's a common destination. And getting that much mass there in one go is serious capability. It really opens up options for customers.
Okay, so that modularity and power are key parts of its tech edge. Let's dive a bit more into what makes Vulcan stand out. You mentioned the BE-4 engines use methane.
Yeah, the BE-4s. Methane is interesting. It's denser than liquid hydrogen, which means basically you can use smaller, lighter fuel tanks on the rocket. Saves weight. Plus, methane engines often burn cleaner and are sometimes seen as, well, more conducive to potential future reuse, though Vulcan's first stage isn't currently designed for recovery like Falcon 9.
So it's a forward-looking fuel choice in some ways.
You could say that, yeah. It offers performance advantages now and maybe pathways for the future.
And it's not just the engines. The whole structure is pretty advanced, too. The fairings.
Right. The payload fairings. They use composite materials, aluminum honeycomb core, graphite epoxy skins. Super strong, but also lightweight. They come in a standard 5.4-meter diameter version and a longer one if needed, maximizing space for big satellites.
And you already touched on the Centaur V upper stage, but that reliability from the RL-10 engines seems like a massive selling point.
Oh, absolutely. You can't overstate it. That proven track record, the precision, the multiple restarts. For complex government missions or sending multi-million-dollar science probes accurately to Mars or the Moon, that demonstrated reliability is gold. It's decades of American know-how built in.
Right. Confidence is key for those missions. And the modular SRBs, as you said, that's not just power. It's also about cost and customization.
Exactly. It lets ULA offer a tailored solution. Need a basic lift, fewer SRBs, lower cost, need maximum grunt, add more SRBs. It gives customers choice and efficiency.
And this isn't all brand new infrastructure, is it? Vulcan leverages existing facilities.
That's a really important point. It's built on a foundation of American aerospace heritage. They use manufacturing facilities in Decatur, Alabama that have roots going back to the Delta rocket program. Yeah. Skilled workforce, established processes.
Continuity.
Right. And it launches from Space Launch Complex 41 at Cape Canaveral in Florida using a clean pad approach designed for rapid turnaround between launches. Yeah. So it benefits from existing infrastructure while incorporating new efficiencies. It's deeply embedded in the U.S. aerospace ecosystem.
Okay, so we know what it is and why it was built. Let's talk about its flight record so far. How does a typical launch go?
Pretty standard sequence, really. Lift off with the BE-4s blazing, plus any SRBs attached. The booster burns through its fuel, separates, falls away. Then the Centaur V upper stage ignites its RL-10s.
And that pushes the payload into orbit.
Either into its final orbit or maybe into a parking orbit first. If it's going further out, like to the Moon, the Centaur performs another burn, the translunar injection, or TLI, to send it on its way.
Got it. And its first flight, the maiden voyage, that was a big one.
Huge. January 8th, 2024. It carried the Peregrine lunar lander.
Part of NASA's CLPS program, right? Commercial Lunar Payload Services.
That's the one. And crucially, Vulcan performed that TLI burn perfectly, sending Peregrine towards the Moon. It was a massive validation right off the bat, showed it could handle complex, deep space trajectories from day one.
Then came the second mission, the certification flight, in October 2024. And this one had a bit of drama.
It did. This flight was all about pushing the rocket, gathering data for certification, and during the ascent, a nozzle on one of the SRBs actually came off.
Oof, that sounds bad.
You'd think so, but here's the incredible part. Despite losing that nozzle, the rocket's control system compensated, kept flying stable, and it still delivered its payload accurately to the intended orbit.
Seriously, even with the chunk falling off.
Seriously. It was actually an amazing demonstration of the rocket's robustness and the sophistication of its flight control software.
So not a failure, but almost a more impressive success in a way. Showed it could handle